Hi folks, we're going to take a look at number 10a from page 213. So they're asking us to find the horizontal asymptote of this function. So I would have probably asked this question differently. I'd just ask you for the end behavior. I wouldn't necessarily give away that there was a horizontal asymptote. So let's see if the idea of having a horizontal asymptote even makes sense. So I look at this function and it looks a lot like a rational function. It's not, because the denominator is not a polynomial, but it is the square root of a polynomial. All right. So when I think about how this function would behave, I would imagine that it would behave like a linear function, because if this square root of 1 doesn't make it, this plus 1 doesn't make much of a difference as time goes on, and so when I think of the square root of x squared, I think of x. So I would imagine that it would behave similarly to a rational function where the numerator and denominator had the same degree. So let's see if that's the case. So the first thing I'm going to do is I'm going to consider the limit as x approaches positive infinity. Okay, so we know that when rational functions have a horizontal asymptote, the behavior is the same on either side. But again, I don't want to assume that because it's not a rational function. Okay, but what I will use is a trick that we used for determining horizontal asymptotes is we divided numerator and denominator by the highest power of x. Now, while I see an x squared plus 1 in the denominator, because I'm square rooting it, I figure the net exponent on this denominator is going to be equal to 1. So the first thing I'm going to do is I'm going to divide numerator and denominator by x. All right, so x over x, which of course is a legal operation to do the same division to numerator and denominator of a fraction. All right, so there we go. Now, in terms of the numerator, nothing special here because I've got just x over x, so that's equal to 1. Now notice I don't have to worry about when x is equal to 0 because I'm talking about end behavior here. I'm just talking about when the x values are very, very large. Okay, the denominator is where I run into a problem. Is I can't break apart this square root. This is not x squared to the 1/2 plus 1 to the 1/2. So there's no way for me to do any direct algebra here. So since I can't get this x squared plus 1 easily out of the square root, what I'm going to do is I'm going to take this x and put it inside the square root. Okay, so let's see how we would do that. So how can I write x as the square root of something? Okay, I realize, I go, well, wait a minute. If I take the square root of x squared, then that's just equal to x. Okay, so what we can do is we can replace x by the square root of x squared and then do the algebra of bringing the two square roots into one square root. Okay, now there is one little issue here because this works out perfectly well when x is positive. Okay, because this is going to give me sort of a positive number when I take the square root of x squared. Okay, so it works great when x is positive, which works great for our scenario because we're looking at x approaching positive infinity. But what happens when we're going to do the other side, when we're going to look at x approaching negative infinity? This is not going to work. Okay, however, what we can do is, so this is if x is greater than 0. What can we do if x is less than 0? Well, that's when we realize, well, we could just take the negative of the square root of x squared. So if I have, say, -4, well, -4 squared is 16. Square root of 16 is 4. So it's just a matter of putting a negative in front. Okay, so this makes me wonder now if things will be different when I look at the limit as x approaches negative infinity. All right, let's take it one step at a time. So we know that when x is larger than 0, as we're looking at here, we can write x as a square root of x. So here we can write x squared plus 1 over, instead of x, the square root of x. Okay, and now, we can use our rules for radicals to bring this under 1 square root. So this is 1 over the square root of x squared plus 1 over x squared. And now I can do my usual algebra. I can distribute the division. Okay, limit as x approaches positive infinity of 1 over, and in the square root here, I'm going to have x squared over x squared, which is 1, plus 1 over x squared. And now I see that as x approaches positive infinity, these are just constant, and that term is just going to be approaching 0. So what do I have? I have that this is just approaching 1 over the square root of 1, which is 1, And so we see that we have a horizontal asymptote of y equals 1 as x approaches positive infinity. Okay? But now let's see what happens when I try to do the limit as x approaches negative infinity. Okay, I'm going to do the same thing. Divide by x. Okay. Okay, but now when I try to replace x with a square root, it's now going to be replaced by the negative square root of x squared. So I have 1 over square root of x squared plus 1 over negative square root of x squared. And so now I think you'll see that we will have a slightly different result. Okay, 1 over, so same thing. I'll bring these two square roots together, but I still have this negative hanging around. So this becomes square root of x squared plus 1, just like before, over x squared. So what do we have? We have negative 1 over square root of 1 plus 1 over x squared. And as before, this term here approaches 0 as x approaches negative infinity, and the whole limit approaches negative 1. Okay, so we actually have two horizontal asymptotes. We have a horizontal asymptote of y equals 1 as x approaches positive infinity. In other words, the limit as x approaches positive infinity is equal to 1, but we also have a horizontal asymptote of y equals negative 1. And this happens as x approaches negative infinity. Or we can write, okay, a nicer way of writing this is that limit as x approaches negative infinity of our function is equal to, that was supposed to be equal to 1, and here it's equal to negative 1. All right? So what we see here is that while this does look like a rational function, we were able to use a trick that worked with rational functions, that the result was similar to what we might expect with a rational function. It didn't quite turn out exactly the same, okay? Because when we looked at the behavior as x approaches negative infinity, we saw that when we tried to write our expression using a square root in order to be able to do some algebra, we had to write it as a negative square root, which produced a different horizontal asymptote, okay? And what you should do is sketch a graph of this function on Desmos, and you should see a horizontal asymptote of 1 as we approach positive infinity, and a horizontal asymptote is negative 1 as we approach negative infinity. All right, that's it for this one.